welcome on Zoom and welcome to our people in the room. It's nice to have the foundation seminar running again with people in person. Today, we're exceptionally lucky. We have Alex Lupsasca, who's currently at the Princeton Gravity Initiative. He was previously associated with Harvard and the BHI, but we unfortunately had to give him away. But it's all right. We've got him back for today. You're in for a real treat. He's a great speaker, and it's a very exciting subject matter. So enjoy, and Alex, take it away.
Thank you very much, Martin, for the very kind introduction and for the invitation. It's a pleasure to be here. So I'll try to live up to the high expectations that have been set. The first half of my talk is going to be an introduction to the black hole photon ring. So some of you here, a lot of you here have already heard about this and you know about it, so you can just enjoy the review or tune out. And then in the second half of the talk, I'll try to discuss some more subtle aspects that probably haven't received as much attention about what it would even mean to see the photon ring experimentally. And I thought that would be an appropriate topic for the foundation seminar. So I always like to start my discussion of the black hole photon ring with this amazing animation from the EHT collaboration, which shows over the years, over the decades, all the successive observations that have led up to the image of M87 that we all know and love. But this really brings to light first how far this black hole is. It's 50 million light years away. And it's not like the EHT discovery arose out of a vacuum. It's actually the product of a very long effort to take successively more zoomed in images of the galaxy M87. And you can see here successive images that zoom in more and more and resolve the image going deeper into the jet, finally until the core is resolved and we can see the black hole. Now, of course, in spite of that, you might think, okay, this is still a little bit blurry, but still it's an amazing achievement that we're able to go all the way to the core and see this image. But of course, at the same time, we're going to keep going and the technology is only going to improve, and there's next generation Event Horizon Telescope that's going to go online in a few years. And hopefully a lot of other experiments will start to do black hole imaging. And so the question is, what are we going to see as the technology improves? And we think that this image that we got in 2019, once we achieve higher resolution, will eventually look more like something like this image, which is a state-of-the-art GRMHD simulation out of the EHD data bank. And this is just one image that comes out of those simulations. There are many, many others. And the really surprising thing about these images is that they all share the same feature, namely that they're dominated by this very narrow and bright ring. And this is really quite surprising. It's a very dramatic feature. The ring is very bright, very thin, and it's present in all the images. So how can that be? If you vary the astrophysical conditions, you can have different kinds of matter. We're not quite sure what's going on around the black hole. And so in the simulations, we vary the astrophysical conditions, but we always get this ring. And so how can that be? And in the first half of the talk, I'm going to give you the answer. So I'll address what is the origin of this ring of light. Then I'll discuss how we can better resolve it and hopefully get an image that resembles the high resolution simulation I just showed you. And third, I'll discuss why I think it's interesting and what we can learn from it. And to give you the punchline, the reason that the ring is always present in all these images is that it's really a gravitational effect. So it's only weakly dependent on the astrophysical details of the source around the black hole. It has to be optically thin, so you have to be able to see through the emission, but roughly that's about it. And beyond that, the ring is a completely universal effect. And in this talk, universal means matter independent. So it just follows from the equations of general relativity and the lensing properties of the black hole. And not only that, but this ring, I'm going to argue, I'm going to show you, if you zoom into it, has a very rich and intricate subring structure. It's actually multiple rings stacked on top of each other. And the relations between these rings are also universal, that is to say, governed by general relativity and controlled by three critical parameters, gamma, delta, tau, which have been computed in the past couple of years, and which are fundamental constants of nature that we hope we'll be able to measure with black hole imaging in the coming decades. Now, the photon ring is present in the image. I just showed you a simulated image, but we don't take images of black holes the way you and I see with our eyes or the way our camera takes pictures. Rather, we use interferometry. And so we really measure the Fourier transform of the image. But I'm going to argue that this photon ring has a strong universal signature, not just in the image, don't just have the narrow ring on the image, but also has a strong signature in Fourier space where we can actually measure with the EHD. And in particular, the signal is present on long interferometric baselines. And the good or bad thing, depending on your perspective, is that I think you really need to go to space to resolve the photon ring. And certainly if you want to measure these exponents, we're going to have to go to space. And the reason I think it's interesting is that, well, okay, so there are many reasons why you might be interested in it, but I think it's remarkable that measuring the photon ring and its detailed shape could give you, in principle, a very stringent test of strong field GR. So the event horizon of a black hole is a visible edge of the universe. You can peer all the way up to it, but not beyond. And the photon ring arises from photons that probe the gravity right outside the event horizon, which is the strongest gravity that's accessible to us, and come to us encoding information about the gravity in that region. And by measuring the shape of the photon ring, I'm going to argue we can get a direct probe into the strong gravity regime outside a black hole at the edge of what we can see. And so I think that's hugely exciting. Let me just mention that after the release of the image in April 2019 by the EHT, there's been an explosion of papers on the photon ring. This is not even a representative sample and very biased, but these are papers by people associated with the BHI, were papers that I thought were particularly good. And they span the gamut from astrophysics to theoretical physics to GR, even to mathematics. There's some really good pure math papers now on the structure of the photon shell. And I think there's going to be a lot more work as we gear up to experimentally measure these rings. Now, my own involvement with this project started here at the BHI with many people presently in the room, like Ramesh and Peter, and probably some people on the call. And this was a very fun project for us, where we really try to dig into the structure of the photon ring and try to start addressing these questions. I've been bringing it up. So I think this is still the best place to start reading up on this topic. And then I had some later work with Samgrala, where we worked out a lot of the mathematical details, if you really care about that. But I think you should start here if you're interested. And that's where I'm going to start as well. So I'll give you a quick overview of what we understood about the structure of the photon ring and how it arises. So the story starts with the photon shell, which is this region of space-time outside a black hole event horizon, where gravity is so strong that light rays can be deflected so much that they go around the black hole multiple times. So there are systems in the sky, like stars, that can weakly lance light rays and bend them a little bit. But when you go around a black hole, and we think probably only when you go around a black hole, it is possible for gravity to get so strong that light rays are deflected so much that they go around in a circle. And in fact, Leo Stein's website has this really cool 3D Java applet where you can simulate these things live. It's very fun to play with. I encourage you to go. And so what's happening in this region is that you're outside the event horizon. So it's possible for signals to escape. But gravity is so strong that light rays can go around and eventually either fall into the black hole or escape back out to infinity, where we can see them. And I want to introduce the critical exponents, which are going to be key in the structure of the photon ring. And the first two are very easy to describe. They're delta and tau. So what are they? If you're here in the photon shell, it's not automatically the case that every light ray goes around, because you can shoot a light ray out and it's just going to go in a pretty much straight line. But if you're in the photon shell and you aim the light ray just right so that it stays on the shell, it's possible to tune it so that in principle it orbits many times, albeit unstably. Now, when it does an orbit, I'm going to define an orbit to be a bounce from the bottom to the top and back. And so a half orbit is just going to be one bounce from the bottom to the top, or vice versa. So for the rest of the talk, that's what I mean by half orbit. So if you have a light ray that's just tuned to stay on the shell, in one half orbit, it's going to sweep out some angle in the azimuthal coordinate phi, and that angle we call delta. And that's going to take some time, tau. So that's a time lapse incurred per half orbit. So hopefully that's clear what delta and tau are. It's just how long it takes and how much you sweep around the black hole in one half orbit. And these are functions of the black hole mass, how big it is, its spin, and the location in the photon shell. And finally, the last actor that we need to introduce is gamma, which is the most exciting critical exponent. And it's a Lyapunov exponent that describes the exponential growth in the geodesic deviation from the bound orbits. So like I mentioned before, these light rays are unstable. The photon can't trap light forever. The light wants to escape, either fall into the black hole or go back out to infinity. And what that means is that if you have a light ray that's on a shell, but not aimed just right, then it's eventually going to escape. And the rate at which it escapes is exponential in the radius. And we can make this very quantitative and show that in 1/2 orbit n, roughly you get this exponential growth, which is governed by gamma, the Lyapunov exponent characterizing the instability of the nearly bound orbits. And again, gamma depends on the mass and spin of the black hole and the position around the photon shell. So these are the three key quantities that are intrinsically defined inside the photon shell as properties of light rays that orbit there. And now we're going to connect that to images that we see and the lensing behavior of the black hole. So to do this, I just need to flash the slide where, if you have never seen this, what does it mean to see an image of something around a black hole? Well, you receive a photon along some light ray. Generically, it's been deflected, but you can imagine that once you receive it with some momentum p phi and p theta, you can translate that into coordinates on a screen perpendicular to the line of sight by imagining that the light ray came to you in a straight line. This is the construction. This is the exact equation. So once you know the momentum of the photon reaching you, you can describe its position on the screen with coordinates alpha beta that were introduced by Bardeen. And the key feature for us of the screen is that it has a very special curve defined on it as a result of there being a black hole in the geometry. And that's this critical curve. So what is this critical curve? Well, if you aim a light ray directly towards the center of the black hole, it's going to fall in. Now the black hole has some gravity. So even if you aim slightly to the side, it's going to pull in light rays and they're going to end up falling in. But if you aim very far to the side, they'll just be weakly deflected, but escape to infinity eventually. So the light rays that you aim all the way to the side can get slightly deflected, but go back out to infinity. The light rays that you aim towards the black hole fall in. And then the question is, what happens on the boundary in between? Those are the critical light rays. And if you aim exactly on this critical curve, then what happens is that the light ray that you shoot back ends up being captured by the gravity of the black hole and asymptotes to an orbit that's bound around the black hole. Now, those orbits are unstable, so it's infinitely hard to tune your light ray to be exactly on this curve. You have to aim infinitely precisely, but in principle, if you do that, you can get a light ray to go around the black hole in the photon shell forever. And there's two things which I think are really interesting about this, at least. So one is that each point around this ring is really a sphere. So these light rays, they really asymptote to a different radius as a function of angle, and they really explore an entire sphere. That's kind of crazy. And the other thing that's crazy is that usually when you look around, say, an image of a star, you're seeing around the star in its geometry. But here you look around the black hole on the image, and you're really seeing different radii in the geometry. And that's the warped nature of space-time really in your face. So going around the image is really going deeper or farther from the black hole, and each point explores that entire sphere. I think there's a lot of tantalizing connections to holography, which are yet to be worked out, but as it is as a GR statement, I think this is really fascinating. Now, to understand the photon ring, what we really care about are these so-called near critical light rays, which are the ones that are not exactly on the curve, because in the real world, you can't quite aim perfectly well. They're the ones that are slightly off to the side. And it's going to be useful to introduce a distance d, which is a perpendicular distance from the critical curve. So when d is slightly positive, you have a light ray that shoots into the photon shell, orbits around many times, and eventually ends up being deflected back out to infinity because it's outside the critical curve. And if you shoot a light ray in with a tiny negative d, then it goes into the photon shell, winds around, and it ends up falling into the black hole because it's inside the critical curve. So these are the light rays that are going to be important to understand the photon ring. And to do that, I have to explain how Kerr black holes lens images. So this image is key And what it shows you is that because of the photon shell, you can have light rays, those that are too near the critical curve, that circumnavigate the black hole multiple times. And as a result, a single point source in the geometry near the black hole can shoot light rays in multiple directions. It will orbit the black hole in different ways, but reach the same observer. And so a single point source can produce multiple images. And to make this perfectly precise, we need to bring in the critical exponents that I just introduced. And in general, this is a complicated story, but this is the simplest example in which you can describe it completely analytically. So let's imagine we're looking down at the black hole from the spin axis, and there's an equatorial disk of sources. And I'm going to show here, so this is the critical curve. And suppose that we're looking at the nth image that we see from light rays that went around m half orbits. So in principle, there's an image that comes at you directly. That's the n = 0 light that just shoots off the disk and comes at you directly. But you can have light that's shot down, and that executes 1/2 orbit. That's this n = 1 light ray, and shows you a whole image of the disk again. Then you can have an n = 2 image that does 2/2 orbits or a full orbit around the black hole and reaches you. In principle, you can have n = 3 and n = 4 and n = 5. And you might think, oh my God, what's happening? It's getting too complicated. But it's actually the opposite. The higher n gets, the easier it becomes. And at high n, there's a simple relation between these images. So if the nth image of the disk is this color wheel with the black curve showing the critical curve, then it's very easy to describe the next image, the n + 1th image. This is why it's a universal property of the black hole, because it depends only on its spin parameters via these critical exponents. And so what's the answer? Well, if this is the nth image, the n + 1th image can be described in a simple way. There's just 3 relevant effects. The first one is that the image gets squeezed in towards the critical curve. So it gets demagnified, and it gets exponentially demagnified by an amount e to the minus gamma. So it gets squeezed in. E to the minus gamma, so gamma is exactly pi in Schwarzschild when the black hole is not rotating. And so this squeezing factor is about 4%. As you spin up the black hole, the demagnification decreases. So you have less of the squeezing effect. And at maximal spin, it's about 9%. So that's one effect. And it's described by this equation, which says that the n + 1th image is exponentially closer by e to the minus gamma. The second effect is that the image rotates. And you can see that here because, well, you have to spend a little bit of time thinking about it, but clearly, if the light ray is shot down, there's kind of a rotation effect associated with that by exactly half a turn. So in Schwarzschild, the color wheel rotates by exactly 180 degrees. But as you spin up the black hole, the light rays in the photon shell get dragged around with it. There's a frame dragging effect. And so as the black hole spin increases, the color wheel rotates more and more until you get to maximal spin, where you get almost 3/4 of a turn. And finally, the last effect is a time delay associated with how long it takes for the light rays to do an additional half turns. And that takes a time tau. And tau is very weakly dependent on the spin of the black hole. It's pretty much 15, 16 times the mass of the black hole. Yeah.
So you got these 3 critical exponents.
Yeah.
They are just numbers, is it? Or are they functions of position on the ring?
So in the general case, they're functions of position on the ring. And so something that would be super duper exciting, although I think it's not the first photon ring experiment we're going to do, but in the longer term, if we could measure 2 successive rings, so we could have this image and then its following image, we'd get to compare at every angle around the ring 3 numbers. So it's not really 3 numbers, but 3 functions.
This is my question.
Yeah. Now, this is the simpler case where we're looking from above and we're seeing only 1 radius in the photon shell, so it's the same number. This is a degenerate example, which makes the math easier. But in the general case, we would get to see multiple numbers. Now, I think for M87, we're at about 17 degrees. And so there's some variation, but it's not huge. And I think if we were able to look at a black hole from the side, then the functions could vary quite a lot, and that would be even more exciting. Thank you for the question. Okay, so I've described these critical exponents. They're properties of the light rays in the geometry, but they also control the lensing behavior of the black hole. And so now we can put it all together and connect back to the images that we simulate of a black hole, like the one I showed you at the start of the talk. So how does that work? Well, the last step is I have to briefly describe ray tracing.
Before you do,
Yeah.
if you had a hotspot located, would anything in the accretion disk be rotated, or only the photons that are in the photon orbit? Only the points, so to speak, from which they were launched on the virtual plane, whatever you call it.
So if you have a hotspot, say you have an accretion disk with a hotspot rotating.
Yeah.
Yeah, so if you fix the observation time, you have to reverse this relation. And so what happens is you can get direct light, which will show you the hotspot at some time, t0. But then if it's been orbiting for a long time, you can also see a lensed image from a light ray that went around the black hole, say once. But there's two effects. One, that light ray rotated around the black hole, it got dragged. And that's described by this. But there's a second effect, which this doesn't describe, which is that at the same time, since you're seeing about tau, which is about 16 m farther into the past, the hotspot presumably wasn't at the same spot. And so there's two different rotation effects going on. One is the frame dragging of the light ray, and separately, there's also the rotation of the source, which moved in that time tau. So yeah, this is a simple stationary disk. If you talk about time-dependent sources, it gets more intricate. But the point remains that I think roughly if you have I guess you can compute the corrections to tau, but I think roughly they should still go like 16 m, at least in the regime of large n. Now, of course, I think what you have in mind is looking at n equals 0 and n equals 1. And I think there the corrections are probably very, very important. And there have been some papers, I think, within EHT looking at that. But I think that's a very, if we could see a hotspot and argue that we saw both the direct image and the lensed image, that would be very exciting, because I think you could claim that's, I don't know if that would be the photon ring, but it's certainly getting into photon ring physics. Okay, so to connect to images, the last step is to describe ray tracing. This is a very intricate subject, but just to give you the cartoon vision, you want to figure out the intensity for each pixel on your screen. So you pick a point alpha beta, you want to compute the intensity at that point. And what you do is you shoot a light ray back from your screen into the geometry. You evolve it using the Nolte-Wiesick equation. And then eventually, the light ray reaches into the source, and that's the black hole, and there's some matter around it. And as it crosses through the matter, the light ray can pick up photons, and you're supposed to load photons onto the light ray according to the local emissivity, how bright the matter is. So this is saying if you take an infinitesimal affine length d sigma along the light ray, you add an infinitesimal intensity di, which is proportional to the emissivity of the matter that you're processing. So the brighter the matter, the more photons you add. And in principle, some of the photons can also get absorbed by the matter. We think for M87, which is likely in the optically thin regime, we can neglect this, but it'll come up again in a second. So you do this, and now you get an intensity along the light ray, and that tells you what the screen brightness should be. And here's the key point. So I told you that if you want to get an additional image, so increase n by 1, you have to go exponentially closer in the distance from the critical curve on your screen. And so if you invert this relation, it directly tells you that the number n of turns that a light ray executes is logarithmically divergent in the distance from the critical curve, d. So as d approaches 0, so you're aiming closer and closer to the critical curve, you get a logarithmically divergent number of turns. And for optically thin matter distributions, which we think is the relevant case for M87, that means there's a mild logarithmic divergence in the observed intensity near the critical curve, because a light ray that executes n turns through the emission will have n times more photons loaded on it. So I is roughly proportional to n is proportional to log d, so I should be roughly proportional to log d. And the photon ring is just a bump in the photon intensity that contains this logarithmic divergence due to near critical orbits. So that's what we mean by photon ring. That's how it arises. And you can see as long as the distribution is optically thin, this argument goes through. It's just a GR argument based on lensing of black holes. And now this is where absorption does come back again. Now in the real world, nothing can really be infinite. And so eventually, if you orbit many, many times, your photons will get reabsorbed. So this doesn't happen forever. You don't really have a divergence. But nonetheless, because the distribution is optically thin, we think this can go on for a long time. And it's been checked in ray traced images of GRMHD simulations that you can get up to n equals 6 photon rings. At least that's how far we went in the state of the art. So to summarize everything I've said, I have this video which shows everything I've told you. So if you have a black hole, generically, you're going to have light rays emitted by stuff around it, which are weakly deflected, but pretty much come at you directly and produce a background image of the emission. So this is the main emission and its direct image, which we call n equals 0. But on top of that, the matter around the black hole can also send light that does a U-turn around it before reaching you, but it has to be aimed more precisely. And so that means that once you get it, it's been lensed into this narrower region. And in principle, you can also have light rays that are aimed even more precisely. They're tuned to do a full orbit around the black holes or 2 half orbits, but because they have to be tuned more sensitively, they end up lensed into an even narrower region, exponentially narrower, and they get this super narrow n equals 2 photon ring. And the full image, of course, is the superposition of all the light rays that you get. So it's the sum of the direct image of the main emission, plus on top the n equals 1, plus the n equals 2 photon ring, and so on and so forth. And so you get an enhancement in the brightness at this location, and that's why you always see a photon ring. Okay. And this has been confirmed by numerical simulations. Everything I told you so far was an analytic argument. But in the state-of-the-art geometry simulations that George Wong ran a couple of years ago, he took a vertical and a horizontal cross-section of the image, and that's shown in blue and red here. And you can see this is the photon ring effect, the brightness enhancement. And if you zoom in on it, it's possible to account for the number of turns that the photons executed around the black hole. And there's a background n equals 0 emission. And then on top of that, n equals 1. And n equals 2 spike, and they get exponentially narrower. But it really works which is great. Okay, so to summarize, there's a photon ring, which is predicted by general relativity to arise in images of a black hole. And it's composed of a sequence of self-similar subrings, with each subring a lensed image of the main emission, indexed by the number n of photon half orbits executed around the black hole. And this arises because of Kerr lensing, which is completely characterized, at least at a large orbit number, by 3 critical exponents, gamma, delta, tau, which I've introduced, and they control the demagnification, rotation, and time delay of successive images. And I think these are great targets for future observation, but it's not the lowest hanging fruit. And what I'm going to argue now in the next half hour is that an interesting thing, which is I think much easier to measure experimentally, is the shape of the photon ring. And I'm not going to dwell on this too much, but we have to be a little bit careful because there's a critical curve, which is a mathematical theoretical curve, but that's not directly what we see. It's not observable. And then there's an observable shape, which is the shape of the photon ring. The photon ring is observable. And the shape of the photon subrings converge to that of the critical curve, and they do so exponentially fast. But at n equals 1, it hasn't really quite converged yet, nor has it at n equals 2. So we have to be a little bit careful because there's a shape of the critical curve, which we can't directly see. And then there's a shape of the photon ring, which is the thing that we can see. And these are not quite exactly the same. But what I'm going to argue now is that there's an interesting experimental proposal for measuring the shape of the n equals 2 photon ring, which would let you make a very precise test of general relativity. So this was proposed in this paper last summer with Sam Garland and Moroni. This is the archive number. And there's some background on the mathematics and the details of the interferometry, and in particular this paper, which I'm now going to dwell on for the next few minutes, because I think there's some really interesting points which connect to foundational questions about what it even means to see a photon ring. So there's really 2 questions here.
Just before you go,
Yeah.
Alex, we've tried a timed seminar, so it's half an hour and then half an hour of discussion.
Ah, sorry.
No,
Okay.
no, that's fine. In your case, maybe just try to wrap up within 10,
Yeah,
15.
great. Then I'll just shoot through this. So there's 2 questions, right? The first one is, how do we measure the shape of the curve in the sky? What does that even mean experimentally? And then once we've answered this, we can ask, okay, so what is the shape of the black hole photon ring? And the main point I want to make is that if you use an interferometer, it's much easier to measure the curve's projected diameter as a function of angle, so how wide the photon ring is. I'm going to explain in detail what this means, but the point is it's not exactly equivalent to seeing the shape. There's a difference, and that's what I really want to highlight, and I think there's all sorts of interesting foundational questions about that. And once I've introduced what the projected diameter means, the upshot will be that the prediction from general relativity for the n equals 2 photon ring of M87 is that it should have the same projected diameter as an ellipse. So if you measure the diameter of the ring as a function of angle, it should obey this functional form to better than 1 part per million. And the precise values of these constants, R1 and R2, which determine the ellipticity of the ellipse, depend on the mass of the black hole, its spin, the emission, the nature of the emission around the black hole. That is not universal, but the functional form of the projected diameter is universal, and that's what should be measured. Okay, so let me briefly flash through this. So if you have a closed curve in the sky, you can parameterize it by normal angle. So here the normal is 0, pi over 2, pi, 3 pi over 2, and you can parameterize the curve by this normal angle. And for an interferometer, this turns out to be a really, really nice thing to do. And in particular, what you can do is once you've defined also the inward pointing unit normal, which I've drawn here in purple, has this equation, you can define the projected position f of phi by this formula. And explicitly, if x and y are the coordinates around the curve, it's this particular function. Okay, this looks simple. Now, why am I doing this? Again, it's because this is the thing you want to get at with your interferometer. This is the relevant observable you want to measure. So how does this work? Well, this projected position, it looks like it's only one function, and it is, but it really encodes information about the full curve. And I just showed this here to convince you. You can invert this relation and reconstruct the curve using this formula. So f of phi, it's one function which encodes all the information about the geometry of the curve. You can reconstruct its shape exactly, but it also encodes all other geometric properties, including, for instance, the radius of curvature, which has this simple form. And just to give you some intuition for this, here are some example of shapes you might be able to draw. And here are the projected positions of these shapes. And this is like a really fun thing you can do. Spend an afternoon playing with these shapes. It's very nice. So this is a circle. This is a Rayleigh triangle, which I'll come to in a second. This is an ellipse. These are the associated f of phi's. And here's a more complicated shape. You can draw whatever function you want. There will be a shape associated with it. And in general, it works also for non-convex curves. You can go negative and get these shapes.
So why does it always close if you?
It has to be periodic.
Oh.
So as long as f of phi is periodic, this will close. Okay, and now this is the key point. This projected position function can always be uniquely decomposed into a part that's parity even and a part that's parity odd. This is the parity even part. This is the parity odd part. And of course, once you have this decomposition, you can recreate the position, that is to say the whole curve, via this relation. But the key point is that these parity even and parity odd parts have a geometric interpretation. The parity even part is the projected diameter. It's the width of the curve at a given angle phi. And the odd part is the centroid motion. And that means any shape, any closed curve in the plane has a decomposition. So if you take f of phi to be this, for instance, which gives you some shape with 5 pointy bits, you can decompose it into a projected diameter, which in this case is just 2. And that's just saying that the width of the curve is the same at every angle. But of course, the shape is not a circle. And that's because as you go around in phi, keeping the width of the curve fixed, you're actually also wiggling the centroid. And you're wiggling it along this shape. So taking a fixed diameter, but rotating it around along this pointy curve gives you this shape. Now notice that if you were to take a flashlight in the plane and cast a shadow of these shapes, then from every angle, the circle casts a shadow of a fixed size, which is its diameter, but so does this function. It's a curve of constant width. Okay, let me flash this. I just wanted to say we can compute the critical curve and its projected position, its projected diameter, and centroid. And the photon rings are close to it, so that's a useful thing to do. And now I'm going to connect this to experiment, which is in an experiment we use interferometry. And what a radio interferometer measures is the correlation between the electric fields measured by two telescopes on Earth. And notice here that what really matters is the projected separation in the plane perpendicular to the line of sight. And once you've defined that, there's also a time delay, tau g, which is associated with how much longer it takes for this signal to reach the telescope relative to this one perpendicular to this line of sight. And it's very important to keep track of this experimentally. And this is very challenging. Now, if you measure these correlations, there's a theorem, the Van Sitter-Zernike theorem, that tells you that what you're really measuring is the Fourier transform of the image. So each telescope pair samples a point U in the Fourier transform of the image, where U is just this projected separation measured in units of the observation wavelength. So if you have multiple satellites on the surface of the Earth, they have different separations. That gives you measurements of V of U at different U. And if you do that enough, you sample the Fourier plane enough, you can reconstruct the full Fourier transform, take the inverse Fourier transform, get the image. And the key point in the paper with Johnson and all, and a lot of the people in this room, is that if you have a ring in the image, which has some width W and diameter D, but you go to the regime where your baseline length is large enough that you've resolved the ring, so it's much bigger than 1 over the diameter, then you see that there's really a ring there. But you haven't gone far enough that you've resolved its width. So the baseline length is in this regime. Then it basically looks like a narrow curve in the sky of the kind I was just describing mathematically. And if that's the case, then there's a simple exercise in Fourier transform theory where you take an infinitely narrow curve, you compute its Fourier transform, and you go to long baselines. So you take I of x to be an infinitely thin narrow curve, compute the Fourier transform and take U to be large. You take it to be in this regime. Then what you get is that the visibility, which is the thing that is actually the direct observable that is measured by your interferometer, takes this functional form. So there's a 1 over root U fall off. There's an overall phase, which depends on the centroid C of phi, the centroid motion of the shape. And then there's 2 oscillating modes, which oscillate with a periodicity that's fixed by D of phi. So remember,
this is the range you want to be in for the shape
yeah,
experiment.
that's right.
So in the subring experiment, a key thing was if you go to very long baseline, then you lose the noise from the lower subring. It's like a 1% effect if you're looking at say 2 or something. So it's 1%. Now, but here you're also looking for 1% effect, right? The deviation from circularity is similarly small. But how do you separate that?
Yeah, so okay. If you have multiple rings, they have different widths WN.
Yeah.
And there's a part of the argument in the paper with Michael and everyone else, which I haven't gone through here, that really says the regime in which this pattern that you get, that's described by this universal formula, it always captures the ring for which U is smaller than 1 over the width WN. But then if you go to U bigger than 1 over WN, where WN is the width of that ring, its signal will die off exponentially fast, which is typically what happens in Fourier transform. And so then you'll be in the regime where you've resolved out that ring exponentially fast, and now you're less than 1 over WN plus 1. And so you're really seeing the pattern for the N plus 1 thing. And I have some slides at the end which show this
Right.
quantitative.
That work for the subring.
Yeah.
But for the shape thing, what?
So for the shape thing, okay, so for the shape thing, we want to see this.
Resolution for 1%. You need a 1% resolution on the shape, right? Okay.
Yeah, so the shape just comes from the fact that if you're in the regime where you see a ring, then there's this ringing pattern, and the periodicity is exactly the diameter of the ring at that angle in Fourier space. So the angle that you're at in Fourier space tells you the diameter of the ring at that angle on the image. And this ringing here, the amplitude is, maybe this is what you're asking about, how much this varies, is set by the relative intensity of the ring at the two endpoints. So this formula tells you that the ringing that you get here is fixed by the diameter of the shape at that angle of R phi, the motion of its centroid, and also these parameters alpha L and alpha right, which are the brightness.
So if they're even, what's that limit?
Yeah, even is the worst. So as you go around the image, the photon ring has a brightness asymmetry, and the amplitude of this ringing will vary. So there's some inclinations at which it's much easier to see than others. But we made a simulated forecast of this experiment, and we found that.
So if they're equal brightness at the opposite ends, then you get a minimum of oscillation?
I think that's how it works. I haven't looked at the detailed equation, but I think that's how it works. Yeah. The key point I wanted to make is that your interferometer, it naturally decomposes your shape, the shape information, into the diameter and the centroid. So that's something that I did mathematically for seemingly no reason. But the point is that the observable that you directly get that in your experiment is this, and it naturally decomposes the centroid. It isolates it as an overall complex phase, and it isolates it from this ringing mode, which depends only on the diameter. And now here's the key thing. The key thing is that it's very hard to keep track of this distance experimentally. So if you want to measure the visibility phase, you have to know exactly how many more phase cycles the light ray that reaches this telescope executed relative to this one. And at the level of precision that the HT operates, if this light ray hits a raindrop of water on the way to the second dish, it bounces around a little bit, that introduces additional phase cycles. Or maybe the experiment heats up and the cables in your experiment dilate, and now there's additional phase cycles in that. And so the upshot is that the visibility phase is extremely hard to measure. It's maybe an order of magnitude harder to measure than the visibility amplitude, which is the norm of this thing. And so what that means is that the lowest hanging fruit for photon ring physics is to measure the magnitude of this signal. And once you take the complex magnitude of it, the centroid motion disappears. Okay, so what I'm telling you is a shape in the sky as a diameter and a centroid, you can describe that mathematically, and it's convenient because your interferometer naturally decomposes the shape information into these two things. And if you have an intensity interferometer, so you only see the amplitude, which is the easiest thing to do. You don't even see the centroid, you only see the diameter. Okay, and so I think this is the foundation seminar. You guys think about these things a lot more than I do, but what does it even mean to see a photon ring if we only measure the amplitude, that is to say, the projected diameter? And an interesting point about this, which was first studied by Euler centuries ago, is that there are many curves with the same diameter d phi. So an example is the circle, which has constant diameter and no centroid motion. And then a Rouleau triangle, which was already studied by Euler. So this shape, if you have a flashlight in the plane, at every angle will cast a shadow of the same diameter, which is that of the circle. So they have the same projected diameter. It's just that this one has a different centroid. By the way, that means you can make bicycles with wheels that are shaped like a Rouleau triangle. And the visibility amplitude alone cannot tell these two things apart. So I think it's very likely that the first measurement of the photon ring, okay, my bet is it's very complicated, but I think it's very likely. Yeah.
I'm not sure I completely buy this final claim.
Okay.
So the diameter you measure essentially from the period, right? Or
yeah,
the wavelength of
yeah.
this oscillation. But even just with amplitude, you also have the size of those fluctuations, right? How large an amplitude do you have in this V versus
yeah, and I claim that tells you about the brightness, the relative brightness between the 2 points at every angle.
Yes, but the Rouleau triangle, I mean, if I just take a simple model like which has got constant intensity all the way around. The circle and the ruler triangle have definitely different projected brightnesses and will be completely distinguishable.
Okay, that's an interesting point. So you're saying if you know, okay, all right,
Yeah.
fine. So let me modify the statement. If these were curves of uniform brightness,
Yes.
then you wouldn't be able to, and you're making the interesting point that if you add in additional information about the relative brightness. Okay, but then you have to assume you already know what that is from the get-go to reconstruct the shape.
No, we should talk about this. At
Yeah,
least to
that's
me.
a very interesting point.
Yeah. It's just that, one guy has got, the vertex has got infinite curvature, right?
Yeah,
And this arc has got, a finite curvature.
yeah.
So when you project, one fellow gives essentially zero intensity and the other guy gives you a lot of intensity. That asymmetry is not present for the surface.
It's going to go into alpha,
Yeah,
alpha,
exactly,
right?
those
Yeah.
guys. And that
It's
will
gonna
tell
go
you
into
what
that.
is the amplitude of your oscillations.
Well, I claimed it's in this formula already, but it's not, it's only going to let you measure d phi and not c of phi. So you have to have an additional relation between you have to say something more other than it's a shape in the sky. Because, okay, let's talk about this afterwards. And the last point I want to make is that for the M87 black hole, if you look at the n equals 2 photon ring in many simulations, there's some caveats there. What you find is that C is some complicated thing, but let's imagine we don't care about it because we're only going to measure visibility amplitude. That's by far the easiest thing to do experimentally. Then it matches the projected diameter of an ellipse. So the ring is not the same shape on a piece of paper as an ellipse, but they have the same projected diameter. And that's what we can easily tell apart. Okay, and I think I'm going to wrap up. The last point I wanted to make, which I think is very interesting, is that if you look at the image, there's the separation between the direct emission, this n equals 0 image, which depends completely on astrophysics. So it's not universal. But once you tell me what the direct emission is, I can paint the photon ring on top of it using what I know about general relativity. It's just these stacked exponentially demagnified images of the main emission. And roughly in the same way, there's a separation between astrophysics and GR in Fourier space where we can measure things between what happens on short baselines, where you're very sensitive to the astrophysics, and what happens on long baselines, where you're mostly sensitive to the photon ring. Okay, and I think I've talked too much. So let me just conclude with this slide. This is not exactly the lowest hanging fruit, but I think this is a really good target to hope for in the future. I certainly hope this is going to happen in my lifetime. So you could imagine an experiment that has a satellite orbiting the Earth. And as it goes around the Earth at each angle of r phi, it measures this visibility. There's a ringing pattern. It looks at the ringing and its periodicity. And what that lets you infer is the projected diameter of the ring at the corresponding angle on the image. So you let your satellite orbit. Every time it goes around, it does a measurement. After enough orbits, you have a good idea of what d phi is at every angle of r phi. And then you can compare it to the prediction from GR, which is that it should follow this functional form that describes the diameter of an ellipse. And you can ask, do your data points match that? And in this paper, we had a forecast, which was a little optimistic because we neglected astrophysical fluctuations, which is something that we're trying to understand now and quantify better. But we thought in principle, this could be a very, very precise experiment to do. And I think this is really exciting. So I'll stop here because I went over time and I'm happy to have a discussion.
Well, thank you very much. I guess we should give priority to people in the room, but if there are questions on Zoom, we will try and get to you. But just so you know, we have a seminar starting in about 10 minutes. So far away in the room.
Well, let me turn it around and ask, assuming that you're interested in measuring the photon ring, there's some people here who are in NGHC. What is the current dream for what we're going to be able to do first? Because I think this is trying to do precision tests of GR, but it's not going to be the first detection of the photon ring. And something I'm really curious about is, what's the fastest way to get there? And I'm sure you guys are thinking about this too.
I think all the experiments you're talking about are space-based.
Yeah.
Right? You want long baselines.
Yeah.
You want to look at n equal to 2, preferably n equal to 1.
But
preferably.
even n equals to 1 would be great.
Would be great, yeah, but that's already going beyond Earth baseline.
Yeah.
NGEHT is going to give huge dynamic range. Peter probably knows more. Whether that dynamic range will buy you extra leverage on the photon ring is something people are debating. Some people
Yeah.
claim they can.
Yeah, so we could get much better, the next generation EHT could get much better UV coverage by a much more extensive array, 21 instead of 8 telescopes on 6 sites, I mean, much more
Yeah.
extensive, with chosen sites to fill in, especially the mid-range of UV distances on the Earth. And so, I mean, one of the questions is, what could we
Has somebody
what can
done
we
it?
see?
Is there an analysis? There's lots of a lot of dispute. Some people thought n equals 1 was already observed. I guess maybe thought that.
This
it
is
what-
exactly the issue.
So could n equals 1 be?
Avery thinks it's already been measured with EHT's 7 telescopes.
Yeah.
And even if he's wrong, if he's right that it is doable, well, then of course with 21 telescopes, it should be a piece of cake. But ultimately the question is, you don't have the angular resolution to really see
a
that
ring.
it's a sharp ring, right? So what you're trying to use is some signal to
Well,
noise.
that's not angular resolution, right? That's sort of radial resolution.
Yeah, but the radial resolution requires a telescope with good angle to tell that the intensity is.
Yeah, yeah.
Yeah, so how can you do it without angular resolution? With enormous signal to noise. So I think there are toy problems where you can show that with infinite signal to noise, you could compensate for inadequate angular resolution. I don't think the final word is in yet, but Andy is absolutely right. Avery
So-
claims to have seen it.
And then you use models. I mean, that's what Avery does, and to compare the observation to different models, and you try to see how they fit.
That's right. It's like what they did in
Mhm,
particle physics before they
right.
had accelerators that could actually.
But I think
produce
there
the
is a,
particles. They
so
don't-
Andy, I think there's an interesting sub-question there. Even if you cannot really tell that there's an infinitely sharp ring
Yeah.
because you don't have angular resolution, maybe you can still tell the shape,
So,
right?
okay,
Shape you can probably do with
Yeah,
engineering. What do you think, Peter?
I think you might be able to.
Yeah, that's worth exploring.
so this is what EHT
Yeah.
did in 2019. And I thought that you can't change the Earth diameter, but I thought there's plans for NGHT to maybe go to 340 gigahertz.
Yes,
Yes.
that will give a little.
So
bit.
that's a 50% increase.
Right.
At that frequency. And so that looks like you almost see the second null. But presumably you would get to 12 gigalambda, maybe 15 lambda, but only along a couple of directions.
Right.
So I think okay, unless I misunderstand, I think the optimistic view is maybe there's like a couple of directions in baseline space where you can see the ringing clearly. And so maybe you can get 2 measurements of d phi, like
Right.
2 angles.
That would be the hope.
That would be the hope. So I think that's that. Okay, I'm naive, but I thought that was kind of the best you could do from Earth. But if you really want to see the full ring, okay, so it's up for debate what it means to see the ring. The point I was making is that d of phi is already not the full ring because it's missing part of the shape information, but it's already really interesting. But I think to see d phi at every angle, you probably need the space satellite, because even if you get lucky and you get a few points at high nulls, you're probably not going to do that at every angle.
Yeah, but I did want to get back to what your proposal there was about the shape. So in the shape, how is I mean, one of the nice things about the subring was all the astrophysics factors out, right?
Yeah.
Because it's I mean, it would be a long time before we get to n equals 2, but at which point, all the astrophysics is done. How does that happen in the shape? Why isn't the shape highly dependent on the details of, can't that be modified by
Yeah. So roughly the idea is that
magnetic fields and stuff like that?
yeah. So the one sentence answer is that the photon rings converge exponentially to the critical curve.
Yeah,
It's e to the minus n away, and when n is 1, you're not very close yet. And so there's significant dependence on the astrophysics. But at n equals 2, Now there's an e⁻² gamma that's really squeezing you very close. And so the difference is tiny. That's why n=2 is really deep into the universal regime. You're really seeing much closer to the critical curve. The deviations are exponentially suppressed. And the n=1 photon ring also has a shape, but you can't predict it just from GR because it's not yet in the universal regime. I mean, I think my hope is that there's going to be an experiment that sees the first photon ring either from Earth in some really clever way or with some satellite in low Earth orbit, and that will motivate, a mission to do n=2. So I think n=2 is going to happen after n=1. But if you have both satellites, suppose you have a way to see the first one and then a way to see the second one, then you can also compare the relative widths, and then you can try to measure gamma, delta, tau. That's super exciting.
The old guys in this room probably won't see it, but you'll see it, Alex.
Well, I
You'll
hope we all see
n=2.
it. I hope we all see it, and I really, okay, NGHT I think is going after a lot of things like accretion flow onto the black hole and Blandford's Nyack mechanism, and I love these things. I think it's really interesting. But if we could squeeze in also, I don't want to wait till I'm
I
60.
mean, it's a different conversation, not for the next 10 seconds, but I'm also interested in whether polarization can help us, pick something out here, indicate separation even of n=0 and n=1. That would be very interesting.
I mean, you guys have done already some work, right? On what polarization does for the different subrates.
So you get these inversions, flips, right?
The things kind of flips and stuff like that.
Yeah.
It's very rich. It's great.
All right, let's thank Alex again.
Yeah, thank you.
We're gonna a couple of minutes.